Andromeda and the local group is what we're talking about today. Now, I think it's an especially interesting topic because we didn't realize that the cluster of stars that we see around us are actually, a majority of them are really just a part of our local galaxy, which is just an island, a gravitational island in the universe. One among hundreds and hundreds of billions, if not trillions, of other galaxies. And a bit player, really, in the larger structure of the universe. And I thought that was pretty awe-inspiring because we didn't know this until I'm looking at it here, less than 100 years ago. So 1923 is when Edwin Hubble found a Cepheid variable, and my audio got screwed up on that episode, but maybe it's still worth checking out the episode on Edwin Hubble I did a few back, and I tried to explain in that one the importance of Hubble's discovery. So we're going to start with the Andromeda Nebula and talk about, from there, branch out to the rest of the galaxies in our local group. And along the way, I'll be using this study guide created by David Butler, who has an entire channel dedicated to teaching people the actual science of astronomy in a very, I'd say a very ASMR-esque tone and style. So I would highly recommend you go check it out. Hopefully with any luck, my future self will remember to put the link in the description. And I'll try to use this book along the way. Visible to the naked eye and studied by Persian astronomers around 900 AD, the Andromeda Nebula was thought to be a part of the Milky Way, which makes you wonder what it is that we used to think our Milky Way was. So I think it's pretty interesting that it's like analogous to being in a cave, and then maybe perhaps other than your echo, you have no idea how big the cave is or what's right in front of you, and for millions of years, if not, at least hundreds of thousands of years, I'm sure we were, as a species, we were looking into the sky and we were seeing the infinite, but we had no context in which to put the stars in. And literally a blink of an eye ago, yesterday, in cosmological, a minute ago in cosmological timescales, we discovered that we're in this galaxy that's 100,000, that takes light 100,000 years to cross, but that's nothing compared to the actual scale of the universe that we're aware of now. And I don't know, I guess I should look into how far away we thought the most distant object prior to that actually was. I think I remember reading something like 200,000 light years. I think that 1,000,000 light years was completely out of the question. So, to me, that's just fascinating that our perspective on the universe has changed so drastically just such a short time ago. It's amazing. But let's move on. Hubble was the guy who initiated the paradigm shift in cosmology, and he found this Cepheid variable. In what he called a nebula at that time. This star altered the course of modern astronomy. The star is called V1. So here's a shot of Edwin Hubble's image of Andromeda, which he made on a 4x5-inch glass plate. It's from October 6th, 1923. He originally identified 3 stars and marked each of them with a N for nova. He thought they were exploding stars, but later he realized that the nova at the top right, the one that says VAR exclamation point, was actually a Cepheid variable. And that's what I'm gonna look up real quick in this book, my encyclopedia. So he, once he realized that, he crossed it out, and he crossed out the N. So the reason he added the exclamation point was because he knew that this variable would allow him to calculate the distance. And of course, that was one of the leading mysteries in cosmology back then. I mean, still really is. Still really is, like, exactly how far away certain objects are. And it blows my mind that we're able to verify with evidence and in a reproducible fashion just how far away Cepheid variables are based on their characteristic periods. And so we know that, let me look it up real quick. So this period of the V1 Cepheid variable star had a period of 31.4 days. And before V1, distances to stars were measured in thousands of light years. But after V1, the universe got much, much bigger. Using his using what I'm about to show you, he realized that the universe, or V1, was over 2.5 million light years away. God, that's so big. So that's amazing that he was measuring it in just thousands or tens of thousands of years, light years. And then all of a sudden the science, the facts that he was so used to, so familiar with working with, and so often gave him just a distance of a couple thousands of light years. It popped out the result of 2.5 million light years. So to me that's so it's like a juxtaposition of the mundane nature of science with the occasional flashes of insight and awe and radical change in perspective that you're given if you stick it out, which took him years to do, by the way. So if it wasn't for his persistence, we would have never known that, or at least it would have taken someone else a lot longer, I'm sure. So here I'm gonna show you a graph. Studying the light curve for V1, Hubble determined its luminosity. I'm gonna try to look it up while I can here. Measuring its apparent brightness here on the Earth, he calculated the distance. So remember that our galaxy is only about 100,000 years wide. So, in that perspective, V1 was definitely too far away to be a part of our galaxy. Classifications, series, Cepheid variables. Okay. Page 42. Getting close. Look at that. I just think that, well, hopefully you guys can see that. That picture is so amazing. I think that is so much more creative than a lot of the CGI that Discovery Channel, the universe and shows like that use nowadays. They're getting better, but to me in particular, I think it's, I don't know, those shows they used to really impress me, but they seem to be just a lot more, what's the word? I don't know, just kind of phoned in and watered down. It's not really as in-depth scientifically as someone like David Butler gets. Okay. So, Cepheid variables here. See if I can make sense of what I'm looking at. here I found a little excerpt about Miss Henrietta Leavitt. In 1908, she was studying the Magellanic Clouds. At that time, the distances of these clouds were unknown. Although we now know that they are neighboring galaxies, 50 kiloparsecs distant. But they were clearly sufficiently remote for all their stars to be considered to be at the same distance. She noticed that the brighter Cepheids had correspondingly longer periods, and because of their equal distance, this showed the existence of a direct link with period and luminosity. So, however, the distance of at least one Cepheid was required to determine the absolute relation for the group. None of them were sufficiently close to show trigonometrical parallaxes, but studies of star clusters in the early 1960s established that the relation reproduced in figure 2.29, which is here it is right here. So I'll try to make this somewhat intelligible. The relationship between, on the y-axis, the vertical axis, was the absolute visual magnitude, and the x or horizontal axis was period in days. So the relationship between these two for classical Cepheids is W Virginis and RR Lyrae stars is what this is. So when you measure the period, it allows its absolute magnitude to be derived, and a measurement of its apparent magnitude then yields the distance of the Cepheid. Wow, that's really, really cool. So there's a tight link between the period, how many days, and it goes all the way from looks like just under 3 days to over close to 100 days for classical Cepheids. And the longer the period, the dimmer the magnitude, the absolute magnitude is. So cool. So I guess it would be analogous, like you do see on those shows, that if a car's headlight is, if we thought of it as, well, maybe a lighthouse would be obviously a better analogy. So if we knew the period of the lighthouse, and we knew that corresponded to, say there were standards set in practice, and maybe there are, that would be really interesting if there are. There's a couple of you out there who are talking about maritime nations and principalities, I guess. I might know the answer to that, but if we knew that the lighthouse rotated, once every 2 minutes, and that was its period, and every lighthouse that has that period is set to a certain standard luminosity, then regardless of how far away you are, you might be able to determine the distance of it. To an approximate distance. Trying to work that out, how that would work. And I suppose it would just be some equation, some function of how much dimmer the light is, how much dimmer it appears to you if you were a ship out at sea than what you know its standard absolute luminosity to be. So if it's just a little bit dimmer, you know that you're much closer to the lighthouse and shore than you might otherwise think. And if it's very, very, very dim, then you have a good idea because the period won't be altered in any way, any significant way, depending on your distance. That period is still consistent, I guess. So that's really cool that that's the one constant that is throughout that phenomenon. So going back to V1 now, that a little light curve showed. V1 was definitely too far away to be a part of it. To be a part of our 100,000 light year galaxy. And this also meant that because it was a part of a nebula, all the other stars in that nebula had to have been that same distance as well. So this made V1 the most important, one of the most important stars in the history of cosmology. I think it's, I don't know, I just can't get enough of that. So Andromeda is a beautiful barred spiral galaxy with two spiral arms that glow with a massive number of new stars. This is a lot like our Milky Way, but it's over twice the width of our galaxy and contains, instead of only about 100 billion, it contains over 1 trillion stars. God, so many. So it's got about 10 times as many stars as our Milky Way does. And light from this magnificent galaxy left its stars over 2.5 million years ago. So when the light that entered Hubble's telescope in 1923 finally made it there, or sorry, when it left its original galaxy or star, humans weren't even evolved yet. Our ancestors were still, I guess, just barely becoming familiar with fires and flintstones. While the light traveled towards Earth, we came into being. Our consciousness in our brains evolved significantly. We changed physiologically. We created and lost great civilizations. And we built telescopes that caught the light when it finally reached our planet. Now Andromeda has I assume all galaxies, has a central black hole Here we see the 100 million solar mass black hole at the center of Andromeda. Its core, really. This is the sharpest visible light image ever made of the nucleus of an entire external galaxy. And you can see here there's a blue glow around the center of what happens to be a double nucleus. And in fact, using the Hubble Space Telescope, astronomers were able to identify the source of the blue light surrounding the supermassive black hole. New spectroscopic observations revealed that the blue light consists of more than 400 stars. Stars are tightly packed in a disk that is only 1 light year across. Put then to perspective, our nearest star to us, to our star, our sun, is 4 light years away, so it's gotta be 0 dark skies if you're a planet on those stars, which I highly doubt. It's not, it wasn't, yeah, I'm sure it's too chaotic to have developed life on those, but that'd be interesting if it did, I suppose. So the disk is nested inside an elliptical ring of older, cooler, redder stars. When the stars are at the farthest point in their orbit, they move slower, so they give the illusion of a second nucleus. Astronomers are trying to understand how apparently young stars were formed so deep inside the black hole's gravitational grip, and how they survive in such an extreme environment. The fact that young stars are so closely bound to the central black hole in our Milky Way, it suggests that it actually might be a common phenomenon in spiral galaxies. So moving on to the local group now. There's a total of 54 galaxies in our local group. Andromeda is the largest. The Milky Way is the second, and Triangulum is the third. All the rest are what we call dwarf galaxies. So most of these are orbiting one of either us or the other 2 large galaxies. Ourselves, we have 16 satellite dwarf galaxies. Andromeda has 25, and the Triangulum might have 1. The other members of the group aren't gravitationally orbiting these larger galaxies. That didn't really make sense, I guess. I don't know where he's going with that one. Here we have the Triangulum, which is also called M33, which is 2.85 million light years away. So it's the 3rd largest member of our local group, with a diameter of about 50,000 light years, so half as wide as our Milky Way, and looks like only 40 billion stars, which is a lot, but only about half as much as we have. Oh, never mind. I guess I'm out of date. It says it's more like 400 billion, so really we have 10 times as many. So this next small irregular galaxy is one of our closest neighbors. It's actually considered prototypical of the earliest fragmentary galaxies that existed in the young universe. What's striking about it is that this NGC 6822 is unusually high, is its unusually high abundance of, I don't know if it's called H, I'm reading it, so H2 or HII, I don't know if that's supposed to be Roman numerals, the region emission nebula. These are visible surrounding the smaller galaxy, particularly towards the upper right. And we can see up there I think it might be those red splotches. Yeah, it is. Okay. So here we have one of them, the glowing gas cloud called Hubble 5 or Hubble V. Has a diameter of about 200 light years, a faint tail of nebulosity trailing off the top of the image. Sits opposite a dense cluster of bright stars at the bottom of the irregularly shaped nebula. Next, IC-10 is about 2.2 million light years away. And this one, Edwin Hubble suspected it might belong to our local group, but it wasn't confirmed until 1996, because it was kind of obscured behind our Milky Way's galactic plane. Here we have the dwarf galaxies, the 16 of them just orbiting our Milky Way galaxy. This map shows the closest dwarfs. They're all gravitationally bound to our Milky Way, which require actually, really interesting that they orbit it, but in a time period of billions of years. So dwarf galaxies typically contain a few tens of millions of stars, which is insignificant compared to the number of stars in our galaxy. Sagittarius dwarf is the closest, and in fact it's interestingly being slowly ripped apart by our galaxy. And the Fornax dwarf is the furthest away and has 6 globular clusters orbiting it. See if I can find a few. So in our book here, it looks like we only have a short section on the local group, but so as we just learned, most of their distances are known. Accurately from measurements of Cepheid variables. The group contains at least a reasonably mixed sample of galaxy types, except that there are no conspicuous giant ellipticals or barred spirals. And it's hard to establish the precise Hubble class for our galaxy because we're inside it. And so we don't easily see its large-scale structure. The galaxy has several small Magellanic clouds. Orbiting us as our small companions. These are the clearly visible ones to the naked eye in the southern sky. And they say that there could be many more DE galaxies. I'm not really sure what DE means. I have to look that up. But there could be many more in the local group, more distant from us and very faint. Let's see what the copyright for this book was. That'll give us an indication of how up to date it is. Although I can't imagine that the science has changed, for our local group at least, much. I can't imagine we've discovered a whole lot, like more things that would fundamentally alter our perspective. Well, interestingly enough, it doesn't have a copyright date on it, but it does say that the constants or the derived data used throughout this book are adopted by the 16th Congress of the International Astronomical Union at Grenoble in 1976. So that does make sense. Because you can see that a lot of the pictures are monochromatic and just straight black and white. So, as of this book, proper motions of galaxies are undetectable. Our only information about their motion through space comes from lost my place. Their line of sight, or radial velocity, and from this it is evident that the local group galaxies are all in orbit around a common center of mass, although observation suggests that the system is not gravitationally stable and will actually break up eventually. Wow, I think it's always really interesting when you learn things like that, because there's so much consistency and constant motion in the skies, and the stars and the planets, and so many rhythmic patterns, so much apparent order, but maybe it's really just chaos that appears to be order because it's observed on such a small time scale by us. For the most distant galaxies in the local group, the distances are not so accurately known, so the membership is uncertain. It's generally assumed that the group includes all galaxies of a distance to 1 megaparsec, which I don't know what a megaparsec is. I guess I could look it up, sure. Well, I want to say it's short for PC. Parsec is the other way around. But it's 3 times 10 to the 13th kilometers. So 1 light year is 0.3 parsecs. So it's roughly light year to parsec is analogous, I guess, to foot to yard or foot to meter. Interesting. Okay, so 1 1 million parsecs would be 3 million light years. Which makes sense, I guess. Okay, let's see if I can find our place again. Here we go. So it's already been mentioned that galaxies near the galactic plane suffer obscuration. So an intrinsically bright nearby galaxy therefore could be heavily reddened and appear faint optically, but it would be brighter in the infrared. Several heavily reddened galaxies are known, some of which are probably in the local group. Alright, so there's some vaguely interesting stuff in there. And so, to return to our study sheet, to us, as I just said, the large and small Magellanic Clouds can be seen in the southern sky. They are, the large is 170,000 light years away. Small is about 200,000. I said 1,000, right? The large, or LMC, for short, is the brightest galaxy in our sky. It contains several billion stars, and many stars are still forming in it. The small Magellanic Cloud, or SMC for short, contains at least several 100 million stars. And like the LMC, there is still a lot of formations taking place in it. So, an interesting little fact about our galaxy is that, based on supernova N63A and 1987A, they were listed about 160,000 light years away. We call that the furthest. Those supernovae are actually in the LMC dwarf galaxy. So 160,000 light years is in fact further beyond the extent of our Milky Way. So, because the large Magellanic Cloud is so close, there's a lot more beautiful nebulae inside it that we can actually see, and we have very detailed pictures of. And this image of supernova remnant 0509 67.5, beautiful name, was made by combining data from two of NASA's great observatories, the Hubble and Chandra X-ray. So the result shows soft green and blue hues of heated material from the X-ray data, surrounded by the pink glowing optical shell, which is representative of the ambient gas being shocked by the expanding blast wave of the supernova. Just, that's amazing. And what's even crazier is that we observe the movement of it. I think that's really cool, the relativity of time. That we can, if we slowed things down a lot, we'd see bacteria living out long, long lives. If we sped everything up a whole lot, we'd see galaxies, entire galaxies and groups, local groups like ours, orbiting like the planets around a star, except much more chaotically and exploding, crashing into each other and exploding, well, I guess not really exploding, but certainly being torn apart, ripped apart. So the star cluster NGC 2074, which is about 170,000 light years away. This region is a firestorm of raw stellar creation, perhaps triggered by a nearby supernova explosion. In the three-dimensional looking image reveals dramatic ridges and valleys of dust, the serpent-head pillars of creation, and gaseous filaments glowing fiercely under torrential ultraviolet radiation. So the region is on the edge of a dark molecular cloud. That is the incubator for the birth of new stars. And lastly, I just wanted to show you that the local group is in fact part of a larger structure known as the local volume. As creative as these astronomers are. And we'll explore this local volume if I get to it.